Hello, my dear students. How are you? I am Professor H.R.Saini. I am with you with a new topic, and today's topic is potential energy stored in a stretched or a compressed spring. When we stretch or compress a spring, we have to do some work. Now, work means energy, and energy can neither be created nor can it be destroyed. Therefore, the work done in stretching or compressing a spring is stored in it in the form of its elastic potential energy. यानी जब हम किसी स्प्रिंग को स्ट्रेच करते हैं या कंप्रेस करते हैं तो हमें कुछ वर्क करना पड़ता है और ये जो वर्क करते हैं क्योंकि वर्क मीन्स एनर्जी एंड एनर्जी कैन नाइदर बी क्रिएटेड नॉर कैन इट बी डिस्ट्रॉयड. So therefore, whatever work is done in stretching or compressing the spring, same is stored in it in the form of its elastic potential energy. Now to derive an expression for the elastic potential energy stored in a stretched or a compressed spring, let us consider a spring whose one end is tied to a fixed support and a mass m or a block of mass m is attached to its other end as shown in the figure. Number 1. Now, in 1, 2 and 3, spring is the same. In the first case, the spring is in its normal length or in the normal state. And in this state, in this position, there is no energy stored in the spring. In the second part, in the second figure, spring is the same, but it has been stretched through a distance x as shown in the figure. And in the third figure, it has been compressed through the same distance x. So therefore, if we have a spring whose one end is connected to a rigid support and a block of mass m is attached to the other end. Now let us suppose it is stretched or compressed through a small distance x. Then, in each case, a restoring force, capital F, is set up in the spring, which tends to take the spring to its equilibrium position, that is the original position. And if F is the restoring force, then, according to Hooke's law, within the elastic limits, F is directly proportional to X, that is, the tension means the force, is directly proportional to extension. Extension means the distance x. Or you can say that F equal to minus kx. Let us call this as equation number 1, where k is the constant of proportionality and is known as the force constant or the spring constant. Its value depends upon the nature of the spring. For a weak spring, its value is small, but for a strong spring, its value is large. अब वीक स्प्रिंग किसको बोलते हैं? ऐसा स्प्रिंग जिसको स्ट्रेच करना या कंप्रेस करना आसान हो उसको बोलते हैं वीक स्प्रिंग. और ऐसा स्प्रिंग जिसको स्ट्रेच करना या कंप्रेस करना मुश्किल हो उसको हम बोलते हैं स्ट्रॉन्ग स्प्रिंग. तो अगर स्प्रिंग वीक है तो के की वैल्यू कम होगी, अगर स्प्रिंग स्ट्रॉन्ग है तो के की वैल्यू ज़्यादा होगी. Now let us suppose we further stretch or compress the spring through a small distance dx. Then some work will have to be done against the restoring force. If dw is the small amount of work done in doing so, then dw equal to dot product of the force F and the small displacement dx, F dot dx. Now, you can see from the figure that F and dx are in the opposite directions. Therefore, angle between F and dx is 180 degree. So, therefore, dw will be equal to F dx cos 180 degree. And cos 180 is minus 1. So, this is equal to minus F dx. Now putting the value of F from equation 1, we get dw equal to, negative sign is there, then F is minus kx into dx. Minus minus become plus, and this is equal to kx dx. This is the small amount of work done in stretching or compressing the spring through a very small distance dx. Let us call this as equation number 2. Now, if capital W is the total work done in stretching or compressing the spring through a distance x, then W can be obtained by integrating equation 2 between the limits 0 to x, that is capital W equal to integral 0 to x dw, and this is equal to integral 0 to x kx dx. Now, as I told you, the value of k depends upon the nature of the spring. Therefore, for a given spring, the value of k is constant, and the constant can be taken out of the sign of integration. So, therefore, w equal to k integral 0 to x dx. Now, this is equal to x square k into x square by 2, and the limits are from 0 to x. Or you can say that w equal to k into upper limit is x. So x square by 2 minus lower limit, that is 0. This is equal to half kx square. Now, this work done on the spring in stretching or compressing it through a distance x is stored in it in the form of its elastic potential energy. And therefore, if capital U is the elastic potential energy stored in the spring, then capital U equal to half kx square. So that is the formula for the elastic potential energy stored in a stretched or a compressed spring. तो जितनी k की वैल्यू ज़्यादा होगी और x की वैल्यू ज़्यादा होगी, उतनी ही उसमें एनर्जी ज़्यादा स्टोर होगी, क्योंकि k की वैल्यू ज़्यादा होने का मतलब कि स्प्रिंग स्ट्रॉन्ग है, उसको स्ट्रेच करना या कंप्रेस करना मुश्किल होगा, तो ज़्यादा वर्क करना पड़ेगा, ज़्यादा एनर्जी स्टोर हो जाएगी. और अगर स्प्रिंग वीक होगा तो हमें वर्क भी कम करना पड़ेगा और एनर्जी भी कम उसमें स्टोर होगी. Now, this implies that for a given spring, because for a given spring half k is constant, so U directly proportional to x square. Now, first I come to the definition of force constant. From equation 1, F equal to kx in magnitude, because I am neglecting the negative sign. Therefore, k equal to F over x. That means the force constant or spring constant of a spring may be defined as the ratio of the restoring force set up in the given spring to the distance through which it is stretched or compressed. Now we can have another definition of spring constant or force constant. If x equal to 1, then k equal to F over 1 equal to F. That means force constant or spring constant of a spring is numerically equal to the force required to stretch or compress it through a unit distance, because I am taking x equal to 1. So we can define the force constant or spring constant of a spring as numerically equal to the force required to stretch or compress it through a unit distance. Now we come to units of force constant or spring constant, because k equal to F over x. Therefore, units of k equal to units of F over units of x. Therefore, in SI, the units of k, that is the force constant or spring constant of a spring, are Newton per meter. And in the CGS system, its units are dyne, because force is in dyne, and distance in centimeters. So dyne per centimeter. Now we come to dimensional formula or dimensions of K, because K equal to force over distance or length, you can say. So therefore dimensions or dimensional formula of K equal to dimensions of force over dimensions of X. Now you know that the dimensions of force are M1, L1, T minus 2, and dimensions of distance or length are L1. L1 goes with L1 and we are left with M1, L0, T minus 2. So this is the dimensional formula of force, M1, L0, T minus 2. Now we come to graph between X and U. We know that the formula for the energy stored in a stretched or a compressed spring is U equal to half kx square. As I told you earlier, for a given spring, k is constant and therefore U proportional to x square. That means the graph between x and U will be a parabola. Now, if x equal to 0, then U equal to 0. If x equal to plus minus x, that is, it can be plus x or minus x, then U will be equal to half k into x square, because if x is positive, then x square is positive, and if x is negative, even then x square will be positive. Therefore, the 3 points will be as shown in the figure. This is for x equal to 0, this is for x equal to plus 1, and this is for x equal to minus 1. On joining these 3 points, we get an upward parabola. So remember the graph between x and U, that means the distance through which the spring is compressed or stretched, and the elastic potential energy stored in the spring is a parabola. So that's all for today. I hope you must have enjoyed my lecture. Please like, share and subscribe to my channel. Thank you very much.